Unit 10. S-block elements. The first element of alkali and alkaline earth metals differs in many respects from the other members of the group. The S-block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only 2 electrons, group 1 and 2 belong to the S-block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium, and francium. They are collectively known as the alkali metals. These are so called because they form hydroxide on reaction with water, which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium, and radium. These elements, with the exception of beryllium, are commonly known as the alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. Among the alkali metals, sodium and potassium are abundant, and lithium, rubidium, and cesium have much lower abundance. Francium is highly radioactive. Its longest isotope, francium-233, have a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the Earth's crust. Strontium and barium have much lower abundance. Beryllium is rare. Radium is the rarest of all, comprising only 10⁻⁻10% of igneous rocks. The general electronic configuration of S-block element is noble gas NS1 for alkali metals and noble gas NS2 for alkaline earth metals. Lithium and beryllium, the first elements of group 1 and group 2 respectively, exhibit some properties which are different from those of the other members of the respective groups. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to the similarity in ionic size and or charge by radius ratio of the elements. Monovalent sodium and potassium ions are divalent. Magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. 10.1 Group 1 Elements Alkali metals. The alkali metals show regular trends in their physical and chemical properties. With the increasing atomic number, the atomic, physical, and chemical properties of the alkali metals are discussed below. 10.1.1 EC. All the alkali metals have 1 valence electrons, NS1, outside the noble gas core. The loosely held s electrons in the outermost valence shell of these elements makes them the most electropositive elements. Metals. They readily lose electrons to give monovalent M+ ions, hence they are never found in free state in nature. 10.1.2 Atomic and ionic radii. The alkali metal atoms have the largest size in a particular period of the periodic table. With increase in atomic numbers, the atom becomes larger. The monovalent ions M+ are smaller than the parent atom. The atomic and ionic radii of alkali metals increases on moving down the group. That is, the increase in size while going from lithium to cesium. 10.1.3 Ionization enthalpy. The ionization enthalpies of the alkali metals are considerably low and decreases down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. 10.1.4 Hydration enthalpy. The hydration enthalpy of the alkali metal ions decreases with increase in ionic size. Lithium has maximum degree of hydration, and for this reason, lithium salts are mostly hydrated. Example, lithium chloride, .2H2O. 10.1.5 Physical properties. All the alkali metals are silvery white, soft, and light metals. Because of the large size, these elements have low density, which increases down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electrons in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electrons comes back to the ground state, there is emission of radiation in the visible region of the spectrum as given below. Lithium gives crimson red color, sodium gives yellow, potassium violet, rubidium red violet, cesium blue color. Alkali metals can therefore be detected by the respective flame test and can be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose its outermost electron. This property makes cesium and potassium useful as electrodes in photoelectric cells. Here you can check that melting point continuously decreases down the group, as well as boiling point also decreases down the group. Density of potassium is less than sodium, and standard electrode potential is highest for lithium and lowest for sodium in that particular alkali group. 10.1.6 Chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group. Reactivity towards air. The alkali metal turns in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxide. They burn vigorously in oxygen forming oxides. Lithium forms monoxide, sodium forms peroxide, the other metal forms superoxide. Superoxide O2- ion is stable only in the presence of large cations such as potassium, rubidium, and cesium. In all these oxides, the oxidation state of alkali metal is +1. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form the nitride, Li3, and as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. It may be noted that although lithium has most negative value of electrode potential, its reaction with water is less vigorous than that of sodium, which has the least negative electrode potential value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia, and alkynes. Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin, lithium at 1073 Kelvin to form hydrides. All the alkali metals hydrides are ionic solids. with high melting points. Fourth, reactivity towards halogens. The alkali metals readily react vigorously with halogen to form ionic halides M plus X minus. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion. The dispersion of electron cloud of the anion by the cation is called polarization. The lithium plus cation is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since anion with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Fifth, reducing nature. The alkali metals are strong reducing agents, lithium being the most and sodium the least powerful. The standard electrode potential, which measures the reducing power, represents the overall changes. It represents the sublimation enthalpy along with ionization and hydration enthalpy. With the small size of its ion, lithium has highest hydration enthalpy, which accounts for its highest negative electrode potential value and its high reducing power. Sixth, solution in liquid ammonia. The alkali metal dissolves in liquid ammonia, giving deep blue solutions which are conducting in nature. The blue color of the solution is due to the ammoniated electron which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Uses. Lithium metal is used to make useful alloys, for example, with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. Used in thermonuclear reactions, lithium is also used to make electrochemical cells. Sodium is used to make sodium lead alloy needed to make lead tetraethane and lead tetramethane. These organolead compounds were earlier used as anti-knock additives to petrol, but nowadays cycles use lead-free petrol. Liquid sodium metal is used as coolant in fast breeder nuclear reaction. Potassium has a vital role in biological system. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. General characteristics of the compound of the alkali metals. All the common compound of alkali metals are generally ionic in nature. General characteristics of some of their compounds are discussed here. Oxides and hydroxides. On combustion and excess of air, lithium forms mainly the oxide Li2O plus some peroxide, lithium peroxide. Sodium forms the peroxide along with some superoxide, while potassium, rubidium and cesium forms the superoxide ammonia. Under appropriate condition, pure compounds of monoxide, peroxide and superoxide may be prepared. The increasing stability of the peroxide or superoxide as the size of the metal ion increases is due to the stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form the hydroxides according to following reactions. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in organic chemistry. The hydroxides, which are obtained by the reaction of the oxides with water, are all white crystalline solids. The alkali metal hydroxide are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. 10.2.2 Halides. The alkali metal halides are all high melting, colorless, crystalline solid. They can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. All of these halides have high negative enthalpies of formation. Values for fluorides becomes less negative as we go down the graph, while the reverse is true for delta H formation for chlorides, bromides and iodides. For a given metal, formation of enthalpy of formation always become less negative from fluoride to iodide. The melting and boiling points always follow the trend fluoride, chloride, bromide, iodide. All these halides are soluble in water. The low solubility of lithium chloride in water is due to its high lattice enthalpy, whereas the low solubility of cesium iodide is due to the smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. Lithium chloride is soluble in pyridine also. Salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Example, carbonic acid, sulfuric acid. The alkali metal forms salts with all the oxoacids. They are generally soluble in water and thermally stable. Their metal carbonates are, and in most cases, the hydrogen carbonates are also highly stable to heat. As the electropositive character increases down the group, the stability of carbonates and hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium being very small in size polarizes a large carbonate ion, leading to the formation of more stable lithium monoxide and carbon dioxide. Its hydrogen carbonate does not exist as a solid. Anomalous properties of lithium. The anomalous properties of lithium is due to the exceptionally small size of its atom and ion, and second, high polarizing power, that is charged by a radius ratio. As a result, there is an increased covalent character of lithium compounds which is responsible for the solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium which has been discussed subsequently. Points of difference between lithium and other alkali metals. Lithium is much harder, its melting point and boiling point are higher than other alkali metals. Lithium is least reactive due to the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxide and nitride, unlike other alkali metals. Lithium chloride is a deliquescent and crystallizes as a hydrate, lithium chloride or 2H2O, whereas other alkali metal chloride do not form hydrates. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements form solid hydrogen carbonates. Lithium, unlike other alkali metal, forms no ethynite on reaction with ethine. Lithium nitrate, when unheated, gives lithium oxide, whereas other alkali metal nitrates decompose to give the corresponding nitrites. Lithium chloride and lithium oxide are comparatively much less soluble in water than the corresponding compounds of other alkali metals. Point of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of the similar size The main points of similarity are both lithium and magnesium are harder and lighter than other elements in the respective groups. Second, lithium and magnesium react slowly with water. Their oxide and hydroxide are much less soluble, and their hydroxide decompose on heating. Both form a nitride by direct combination with nitrogen. The oxide of lithium monoxide and magnesium oxide do not combine with excess oxygen to give any superoxide. The carbonate of lithium and magnesium decompose easily on heating to form the oxide and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Both lithium chloride and magnesium chloride are soluble in ethanol. Both lithium chloride and magnesium chloride are deliquescent and crystallizes forms aqueous solution as hydrates, lithium chloride or 2H2 and magnesium chloride or 6H2O. 10.4 Some important compounds of sodium. Industrially, important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride, and sodium bicarbonate. The large scale production of these compounds and their uses are described below. Sodium carbonate, also known as washing soda. Sodium carbonate is generally prepared by solvay process. In the process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia. When ammonium carbonate followed by the ammonium hydrogen carbonate are formed, the equation for the complete process may be written as sodium bicarbonate crystal separates. These are heated to give sodium carbonate. In this process, ammonia is recovered when the solution containing ammonium chloride is treated with calcium hydroxide. Calcium chloride is obtained as a byproduct. It may be mentioned here that solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Sodium carbonate is a white crystalline solid which exists as a decahydrate. This is also called washing soda. It readily is soluble in water. On heating, the decahydrate loses its water. Of crystallization, it forms monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to white powder called soda ash. Carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. Uses: it is used in water softening, laundering and cleaning. It is used in the manufacture of glass, soap, borax and caustic soda. It is used in paper, paints and textile industries. It is an important laboratory reagent both in qualitative and quantitative analysis. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of the salt. In tropic countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lactons of salts are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride and magnesium chloride are impurities because they are deliquescent, absorb moisture easily from the atmosphere. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separates out, calcium and magnesium chloride being more soluble, then sodium chloride remains in solution. Sodium chloride melts at 1081 Kelvin. It has a solubility of 36 gram on 100 gram of water at 273 Kelvin. The solubility does not increase appreciably with increase in temperature. It is used as a common salt or table salt for domestic purpose. It is used for the preparation of sodium peroxide, sodium hydroxide and sodium carbonate. Sodium hydroxide, caustic soda. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in cast and candle cell. A brine solution is electrolyte using a mercury cathode and a carbon anode. Sodium metal discharge at cathode combines with mercury to form sodium amalgam. Chlorine gas is evolved at the anode. The amalgam is treated with water to give sodium hydroxide and hydrogen gas. Sodium amalgam plus water will give us sodium hydroxide, mercury and hydrogen gas. Sodium hydroxide is a white, translucent solid. It melts at 591 Kelvin. It is readily soluble in water to give a strong alkaline solution. Crystal of sodium hydroxide are deliquescent. The sodium hydroxide solution at the surface reacts with carbon dioxide in the atmosphere to form sodium carbonate. Uses: it is used in the manufacture of soap, paper, artificial silk and a number of chemicals. In petroleum refining and the purification of bauxite. In the textile industry for mercerizing of cotton fabrics, for the preparation of pure fats and oils and as a laboratory reagent. Sodium bicarbonate, baking soda. Sodium bicarbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide, leaving holes in cakes or pastries and making them light and fluffy. Sodium bicarbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. Sodium bicarbonate is a mild antiseptic for skin infections. It is used in fire extinguisher as well. Biological importance of sodium and potassium. A typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on the outside of cells, being located in plasma, blood plasma, and in the interstitial fluid which surrounds the cells. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transport of sugars and amino acids into cells. Sodium and potassium are also so similar chemically, differ quantitatively in the ability to penetrate cell membranes, in the transport mechanism, and in their efficiency to activate enzymes. Thus, potassium ions are the most abundant cations within cell fluids, where they activate many enzymes, participate in the oxidation of glucose to produce ATP, and with sodium are responsible for the transmission of nerve signals. There is a very considerable variation in the concentration of sodium and potassium ions found on the opposite side of cell membranes. As a typical example, in blood plasma, sodium is present to the extent of 143 millimole per liter, whereas the potassium level is only 5 millimole per liter. Within the red blood cells, these concentrations changes to 10 millimole per liter of sodium plus and 105 millimole per liter of potassium plus. The ionic gradient demonstrates a discriminatory mechanism called sodium-potassium pump, operates across the cell membrane, which consumes more than 1/3 of the ATP used by a resting animal and about 15 kg per 24 hours in a resting human. 10.6 Group 2 elements, alkaline earth metals. The group 2 element comprises beryllium, magnesium, calcium, strontium, barium, and rhodium. They follow alkali metals in the periodic table. These, except beryllium, are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members and shows diagonal relationship to aluminium. The atomic and physical properties of the alkaline earth metal are shown in table 10.2. EC. These elements have 2 electrons in the s orbital of the valence shell. Their general EC may be represented as noble gas and S2. Like alkali metals, the compounds of these elements are also predominantly ionic. 10.6.2 Atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the alkali metals in the same periods. This is due to the increased nuclear charge in these elements. Within the group, the atomic and ionic radii increases with increase in atomic number. 10.6.3 Ionization enthalpy. The alkaline earth metal have low ionization enthalpy due to fairly large size of the atom. Since the atomic size increases down the group, the ionization enthalpy decreases. The first ionization enthalpies of the alkaline earth metals are higher than those of the corresponding group 1 metal. This is due to the small size as compared to the corresponding alkali metals. It is interesting to note that the second ionization enthalpy of the alkaline earth metal are smaller than those of the corresponding alkali metals. Hydration enthalpies. Like alkali metals ions, the hydration enthalpy of alkaline earth metal ions decreases with increase in ionic size of the group. The hydration enthalpy of alkaline earth metal ions are larger than those of alkali metal ions. Those compounds of alkaline earth metals are more extensively hydrated than those of alkali metal. Example, magnesium chloride and calcium chloride exist as magnesium chloride.hexahydrate and calcium chloride.hexahydrate, while sodium chloride and potassium chloride do not form such hydrates. Physical properties: the alkaline earth metal in general are silvery white, lustrous, and relatively soft, but harder than alkali metals. Beryllium and magnesium appear to be somewhat grayish. The melting and boiling point of these metals are higher than the corresponding alkali metal due to smaller size. The trend is, however, not systematic because of low ionization enthalpies. They are strongly electropositive. In nature, the electropositive character increases down the group from beryllium to barium. You can have a look over the melting point and boiling point, as these are not systematic. You can check it. You have to memorize it because these can be asked in your competitive exams. Calcium, strontium, and barium impart characteristic brick red, crimson, and apple green colors, respectively, to the flame. In flame of the electrons are excited to higher energy levels, and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The flame test for calcium, strontium, and barium is helpful in the detection in the qualitative analysis and estimation by flame photometry. The alkaline earth metal, like those of alkali metals, have high electrical and thermal conductivities, which are typical characteristic of metals. Chemical properties. The alkaline earth metals are less reactive than the alkali metals. The reactivity of these elements increases on going down the graph. Reactivity towards air and water. Beryllium and magnesium are kinetically inert and to oxygen and water because of the formation of an oxide film on the surface. However, powdered beryllium burns brilliantly on ignition in air to give beryllium oxide and beryllium nitride. Magnesium is more electropositive and burns with dazzling brilliance in air to give magnesium oxide and magnesium nitride. Calcium, strontium, and barium are readily attacked by air to form the oxide and nitride. They also react with water with increased vigor even in cold to form hydroxides. Reactivity towards the halogens. All the alkaline earth metals combine with halogen at elevated temperature, forming their halides. Thermal decomposition of ammonium. Beryllium fluoride is the best route for the preparation of beryllium fluoride, and beryllium chloride is conveniently made from the oxide. Reactivity towards the hydrogen. All the elements except beryllium combines with hydrogen upon heating from their hydrides MH2. Beryllium hydride, however, can be prepared by the reaction of beryllium chloride with lithium aluminium hydride, which is a reducing agent. Reactivity towards acid. The alkaline earth metals readily react with acids liberating dihydrogen. Reducing nature, like alkali metals, the alkaline earth metals are strongly reducing agents. This is indicated by large negative value of their reduction potential. However, their reducing power is less than those of the corresponding alkali metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy associated with the small size of beryllium ion and relatively large value of the atomization enthalpy of the metal. Solution in liquid ammonia. Like alkali metals, the alkaline earth metal dissolve in liquid ammonia to give deep blue-black solutions of the forming ammoniated ions. From these solutions, the ammoniates MH3 2+ can be recovered. Uses. Beryllium is used in the manufacture of alloy. Copper beryllium alloy are used in the preparation of high-strength spring. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloy with aluminium, zinc, manganese, and tin. Magnesium aluminium alloys, being light in mass, are used in aircraft construction. Magnesium powder and ribbon is used in flash powders and bulbs, incendiary bombs, and signals. A suspension of magnesium hydroxide in water called milk of magnesia is used as an antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metal from oxide, which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperature, have often used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example in the treatment of cancer. General characteristics of compounds of the alkaline earth metal. The dipositive oxidation state M2+ is the predominant valence of group 2 elements. The alkaline earth metal form compounds which are predominantly ionic but less ionic than the corresponding compounds of alkali metals. This is due to increased nuclear size and smaller size. The oxide and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large-sized members, calcium, strontium, barium. General characteristic of some of the compounds of alkaline earth metals are described below. Oxide and hydroxide. The alkaline earth metal burns in oxygen to form the monoxide, ammo which, except for beryllium oxide, have rock solid structure. The beryllium oxide is essentially covalent in nature. The enthalpy of formation of these oxides are quite high, and consequently they are very stable to heat. Beryllium oxide is amphoteric, while oxides of other metals are ionic in nature. All these oxides except beryllium oxide are basic in nature and react with water to form sparingly soluble hydroxides. The solubility, thermal stability, and the basic characteristic of these hydroxides increases with increasing atomic number from magnesium hydroxide to barium hydroxide. The alkaline earth metal hydroxides are, however, less basic and less stable than alkali metal hydroxide. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. Halides, except for beryllium halide, all other halide of alkaline earth metal are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvent. Beryllium chloride has a chain structure in the solid state as shown below, and in the vapor phase, beryllium chloride tends to form chloro-bridge dimer which dissociate into the linear monomer at higher temperature of the order of 1200 Kelvin. The tendency to form halide hydrate gradually decreases. For example, magnesium chloride .8H2O, calcium chloride .6H2O, strontium chloride .6H2O, and barium chloride .2H2O. Now the graph. The dehydration of hydrated chloride, bromide, and iodide of calcium, strontium, barium can be achieved on heating. However, the corresponding hydrated halide, barium, and magnesium on heating suffer hydrolysis. The fluorides are relatively less soluble than the chloride owing to their high lattice energies. Salts of oxoacids. The alkaline earth metals also form salts of oxoacid. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of a sodium or ammonium carbonate solution to a solution of a soluble salt of these metals. The solubility of carbonate in water decreases as the atomic number of the metal ion increases. All the carbonate decomposes on heating to give carbon dioxide and the oxide. Beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increases with increasing cationic size. The sulfates of the alkaline earth metal are all white, solid, and stable to heat. Beryllium sulfate and magnesium sulfate are readily soluble in water. The solubility decreases from calcium sulfate to barium sulfate. The greater hydration enthalpies of barium 2+ and magnesium 2+ divalent overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water. The nitrates are made by dissolution of the carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as an anhydrous salt. This again shows a decreasing tendency to form hydroxide with increasing size and decreasing hydration enthalpy. All of them decompose on heating to get the oxide like lithium nitrate. Solubility of alkaline earth metal hydroxide in water increases down the graph. Solubility of alkaline earth metal carbonate and sulfate in water decreases down the graph. Anomalous behavior of beryllium. Beryllium, the first member of the group to metal, shows anomalous behavior as compared to magnesium and rest of the members. Further, it shows diagonal relationship to aluminium, which is discussed subsequently. Beryllium has exceptionally small atomic and ionic size and thus does not compare well with other members of the group. Because of the high ionization enthalpy and small size, it forms compounds which are largely covalent and get easily hydrolyzed. Beryllium does not exhibit coordination number more than 4. In its valence shell, there are only 4 orbitals. The remaining members of the group can have a coordination number of 6 by making use of d orbitals. The oxide and hydroxide of beryllium, unlike the hydroxide of other elements in the group, are amphoteric in nature. Diagonal relationship between beryllium and aluminium. The ionic radii of Be2+ is estimated to be the 31 picometer. The charge ratio is nearly the same as that of aluminium travalent cation. Hence, beryllium resembled aluminium in some ways. Some of the similarities are: like aluminium, beryllium is not really attacked by acids because of the presence of an oxide film on the surface of the metal. Beryllium hydroxide dissolves in excess of alkali to give a berylate ion, BeOH4 2-, just as aluminium hydroxide gives aluminate ion. The chloride of both beryllium and aluminium have chloride-Belch chloride structure in vapor phase. Both the chloride are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts catalysts. Beryllium and aluminium ions have strong tendency to form complex. Some important compound of calcium. Important compound of calcium and calcium oxide, calcium hydroxide, sulfate, calcium carbonate, and cement. These are industrially important compounds. The large-scale preparation of these compounds and the uses are described below. Quicklime, calcium oxide. It is prepared on a commercial scale by heating limestone in a rotary kiln at 1070 to 1270 Kelvin. The carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Calcium oxide is a white amorphous solid. It has a melting point of 2870 Kelvin. On exposure to atmosphere, it absorbs moisture and carbon dioxide. The addition of limited amount of water breaks the lumps of lime. This process is called flaking of lime. Quicklime slaked with soda gives soda lime. Being a basic oxide, it combines with acidic oxide at high temperature. It is an important primary material for manufacturing cement and is the cheapest form of alkali. It is used in the manufacture of sodium carbonate from caustic soda. It is employed in the purification of sugar and in the manufacture of dyestuff. Flake lime, calcium hydroxide. Calcium hydroxide is prepared by adding water to quicklime. It is white amorphous powder. It is sparingly soluble in water. The aqueous solution is known as lime water, and the suspension of slake lime is in water is known as milk of lime. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. On passing excess of carbon dioxide, the precipitate dissolves to form calcium bicarbonate. Milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. Uses. It is used in the preparation of a mortar, a building material. It is used in whitewash due to its disinfectant nature. It is used in glass making and tanning industry for the preparation of bleaching powder and for purification of sugar. Calcium carbonate occurs in nature in several forms like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slake lime or by the addition of sodium carbonate to calcium chloride. Excess of carbon dioxide should be avoided since this leads to the formation of water-soluble calcium hydrogen carbonate. Calcium carbonate is a white, fluffy powder. It is almost insoluble in water. When heated to 1200 Kelvin, it decomposes to evolve carbon dioxide. It reacts with dilute acid to liberate carbon dioxide. Uses. It is used as a building material in the form of marble and in the manufacture of quicklime. Calcium carbonate along with the magnesium carbonate is used as a flux in the extraction of metals such as iron, especially precipitated. Calcium carbonate is extensively used in the manufacture of high quality paper. It is also used as an antacid, mild abrasive in toothpaste, a constituent of chewing gum, and a filler in cosmetics. Calcium sulfate, POP, plaster of Paris, is a hemihydrate of calcium sulfate. It is obtained when gypsum calcium sulfate .2H2O is heated to 393 Kelvin. Above 393 Kelvin, no water of crystallization is left and anhydrous calcium sulfate is formed. This is known as dead burnt plaster. It has a remarkable property of setting with water on mixing with an adequate amount of water. It forms a plastic mass that gets into hard solid in 5 to 15 minutes. The largest use of POP is in the building industry as well as plasters. It is used for immobilizing the affected part of organ where there is a bone fracture or sprain. It is also employed in the dentistry, in ornamental work, and for making cast of statues and busts. Cement is an important building material. It was first introduced in England in 1824 by Joseph Aspden. It is also called Portland cement because it resembles with the natural limestone quarried in the Isle of Portland, England. Cement is a product obtained by combining a material rich in lime with other materials such as clay, which contains silica, along with the oxide of aluminium, iron, and magnesium. The average composition of Portland cement is calcium oxide 50 to 60%, silica 20 to 25%, aluminium oxide 5 to 10%, magnesium oxide 2 to 3%, iron oxide 1 to 2%, and sulfur trioxide also 1 to 2%. For a good quality cement, the ratio of silica to alumina should be between 2.5 and 4, and the ratio of lime to the total of oxides of silicon, aluminium, and iron should be also as possible to 2. The raw material for the manufacture of cements are limestone and clay. When a clay and lime are strongly heated together, they fuse and react to form cement clinker. The clinker is mixed with 2 to 3% by weight of gypsum to form cement. Those important ingredients present in Portland cement are dicalcium silicate 26%, tricalcium silicate 51%, and tricalcium aluminate 11%. Setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to the hydration of the molecule of the constituents and their rearrangement. The purpose of adding gypsum is only to slow down the process of setting of the cement so that it gets sufficiently hardened. Uses. Cement has become a commodity of national necessity. For any country next to iron and steel, it is used in concrete and reinforced concrete and plastering and the construction of bridges, dams, and buildings. Biological importance of magnesium and calcium. An adult body contains about 25 grams of magnesium and 1200 grams of calcium, comparatively with only 5 grams of iron and 0.06 grams of copper. The daily requirement in the human body has been estimated to be 200 to 300 milligrams. All enzymes that utilizes ATP and phosphate transfer require magnesium as a cofactor. The main pigment for the absorption of light in plant is chlorophyll, which contains magnesium. About 99% of body calcium is present in bones and teeth. It also plays important roles in neuromuscular functions, interneural transmission, cell membrane integrity, and blood coagulation. The calcium concentration in plasma is regulated at about 100 mg per liter. It is maintained by two hormones, calcitonin and parathyroid hormone. You know that bone is not an inert and unchanging substance, but is continuously being solubilized and redeposited to the extent of 400 mg per day in man. And all these calcium passes through this plasma. Summary. The S block of the periodic table constitute group 1 and group 2. They are so called because their oxide and hydroxide are alkaline in nature. The alkali metals are characterized by 1s electron and the alkaline earth metal by 2s electrons in the valence shell of the atoms. These are highly reactive. Metal forms monopositive and dipositive ions respectively. There is a regular trend in the physical and chemical properties of the alkali metal. With increasing atomic number, the atomic and ionic sizes increases and the ionization enthalpy decreases systematically down the graph. Somewhat similar trend are observed among the properties of alkaline earth metals. The first element in each of these groups, like lithium in group 1 and barium in group 2, show similarities in properties to the second member of the next group. Such similarities are termed as the diagonal relationship as in the periodic table. As such, These elements are anomalous as far as their group characterization are concerned. The alkali metals are still very white, soft, and low melting. They are highly reactive. The compounds of alkali metal are predominantly ionic. The oxide and hydroxide are soluble in water, forming strong alkalis. Important compounds of sodium include sodium carbonate, chloride, hydroxide, and bicarbonate. Sodium hydroxide is manufactured by Castner-Canel process, and sodium carbonate by Solvay process. The chemistry of alkaline earth metal is very much like that of the alkali metal. However, some difference arises because of reduced atomic and ionic size and increases cationic charges in case of alkaline earth metal. The oxide and hydroxides are less basic than the alkali metal oxide and hydroxide. Industrially important compound of calcium include calcium oxide, hydroxide, sulfate, POP, calcium carbonate, limestone, and cement. Portland cement is an important constructional material. It is manufactured by heating a pulverized mixture of limestone and clay in a rotary kiln. The clinker thus obtained is mixed with some gypsum, 2 to 3% to give a fine powder of cement. All these substances find variety of uses in different areas. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of iron balance and nerve impulse conduction.